Okay. So today we're going to talk about trig integrals, and then maybe at the end we'll get to trig substitutions. Um, so real quick, let's just recap a little bit of what we talked about yesterday. And there was a couple of examples that we didn't get to. So I kind of want to at least just mention those and then maybe talk about the approach of how you would solve those. And I'll leave those to you guys to work out the rest for practice. So yesterday, we did integration by parts. And so a couple of examples that we didn't see. There is one that looks like this. It's a rational expression with a square root. And so when you see a problem like this, you should kind of first think, we always want to kind of go through your checklist. And as we learn more techniques of integration, you'll run through each technique and hopefully get good at looking ahead and being able to recognize types of integrals and understanding what techniques work well with each type. This is actually a type of integral that would work well with what's called a trig substitution, which maybe we'll touch on by the end of today, if not tomorrow for sure. But at the moment, we can't quite integrate it. If we look to use a u sub, usually when we make a u substitution, we need to get rid of things like sums underneath a square root. Whenever we have a sum of terms underneath a square root, in particular, a sum of things like a constant and a quadratic, those don't work well. Those are very hard to integrate, and we require techniques and substitutions in order to do so. The problem is that we have an r squared in the denominator. So if we have an r squared in the denominator, if we make our u something like 4 plus r squared, then the differential is going to be on the order of r. And the problem is we have an r cubed in the numerator. So how do we do this? We can actually do a combination of integration by parts and u subs. As we were just saying, we want to get rid of this typically with a u sub, but we need to make sure the corresponding differentials also substitute in order to complete the integral. So what we might want to do, if we are going to do integration by parts, is we've got our u and our dv. And well, we want to look, which term do we want to integrate? Which term do we want to differentiate? What's the problem of differentiating square roots? Hopefully you haven't had calc too long ago, or if you have, take some derivatives of square root functions and recall how that goes. The problem with taking derivatives of square roots is that we get more and more square roots. And it will get, even if we have it as a negative square root, so this we can consider 4 plus r squared to the minus 1/2. If I keep taking derivatives, we'll keep having more negative powers, negative fractional powers in particular. So ideally, we actually want to be able to integrate that term. But as I was kind of mentioning, if we were to do it with a u sub, we need only a single power of r in the numerator. So what we want is something like this. This is a nice term we can integrate, at least with some u substitutions. And we may want to choose a different variable than u. Of course, with integration by parts, our formulas, we like to use u and v's as well. And then our u, we would make as r squared. And our du is easy enough to compute. And then it's the v that within the integration by parts, we're going to have to do a U substitution. So check that on your own. Check setting W equal to the radicand, the term underneath the square root. And then if I make that substitution within here, I can integrate that and then use that as a piece for integration by parts. So check those on your own. Ask any questions if you want after you've tried to work through it, either in office hours or before or after class if you want to talk about it. The other example I wanted to mention was something like if we wanted to integrate x natural log of x. Now, using integration by parts, again, why is the integration by parts just jump out at us here? Well, we have a product. We could look to use any sort of U sub, but again, the natural substitution we would want to make is natural log. And with natural log, the differential has 1 over x. And since we don't have a 1 over x, the other x that appears is in the numerator, a U sub isn't going to work terribly well in this case. So our next guess would be integration by parts. And since we do have a product, integration by parts seems like a natural thing to at least check and see if it'll help us. But there's one problem here with integration by parts, at least in terms of the caveats that we were talking about yesterday. And namely, what happens with a polynomial times a natural log? We saw a few examples yesterday of polynomials times exponential, polynomials times a trig function. And I mentioned that almost always you want to differentiate that polynomial part. Why is that? It's nice when we take derivatives of polynomials because the degree of the polynomial decreases. And eventually, if we keep doing integration by parts, we can decrease that degree of polynomial to 0. So we can entirely get rid of that out of our term that we need to integrate. The problem is, what's going to happen if we take our u equal to x? Well, it's nice enough because then our du is dx. But what about our v? Excuse me, our dv? Then our dv itself is natural log of x, which, as we saw yesterday, we needed an integration by parts term technique to integrate. So in this case, it's almost making it harder for ourselves because we would need to use integration by parts within an integration by parts. And moreover, if you tried to do that, it wouldn't necessarily make the integral much easier. So if you remember from yesterday, our integral of natural log of x was x natural log of x minus x. And now if I try to integrate v du within the integration by parts formula, what's going to happen? Did it get any easier? We still have the exact same term. So it's not helping. So this happens a lot with integration by parts. I don't want you guys to get lulled into a sense of ease by any means, especially with the examples I've done, because I mean, I've done this plenty of times. I know how to integrate these. I can see and think ahead of what's the best way. This happens a lot, especially with integration by parts. It's a lot of guess and check to see whether the terms that you set as your u and dv, whether or not they'll work out. So don't be shied away. Don't get discouraged if you try something and you look at it and then see that is really messy, really complicated. It's not going to help us. Try to think of a different example or a different way of approaching it. Well, in this case, there's only one other way, and it's going to go counter to the techniques we were using yesterday, or at least the principle, in terms of, well, if we have our polynomial term as our dv, and our natural log as our u, what's that going to look like? Well, we can take a derivative of natural log. That gives us 1 over x. And I can integrate x, even though it's getting a higher power, it's looking a little more complicated. Well, now what's going to happen when we plug it into our formula? Our u, v, easy enough to multiply, and then what goes underneath the new integrand is going to be v du. And nicely enough, when we multiply v and du, even though we have an x in the denominator, we multiply it with 2 powers of x in the numerator. They divide out and then give us a nice polynomial to complete that last integrand.
Shouldn't v be x squared over 2?
Yeah, sorry, I forgot my constant there. So try those on your own, finish those, and then let me know if you have any questions. So let's take a look now at trig integrals. So trig integrals are fairly easy in terms of the types of integrals we have to do. We want to start with essentially just integrating different powers of trig functions. So the best way to really teach this is just to see examples with these. We want to integrate things like cosine cubed of x. So how do we do that? Just as a quick reminder, quick review, hopefully this is all ingrained by now, but we have our Pythagorean identities. And then we can derive any of the other ones that we need to. So tangent squared x is equal to secant squared minus 1 and then of course there's cosecant, cotangent identities as well. These are the two main ones. I think these are the ones that come up most. The other ones, very similar, except with minus signs that are off. So how do we integrate cosine squared, or excuse me, cosine cubed of x? The idea is that the derivatives of sine and cosine always alternate up to a minus sign. And so we can use our Pythagorean identities to change a certain number of powers, usually an even number of powers, from cosines to sines and vice versa. And so if I have an integral with only cosines, we can create sines by using our Pythagorean identities. And then hopefully, if the powers are nice enough, we can make a u substitution, and the extra powers that we need to substitute out will then be taken care of in our differential. So let's see what I mean by that. So if I have 3 powers of cosine, that's going to be cosine squared times cosine. And we can convert 2 powers of cosine into 1 minus sine squared. How does that help us? Well, this term we can just integrate. We know how to integrate 1 power of cosine. And now our other term has 2 powers of sine and only 1 power of cosine. So our two integrals here, integral of cosine, I'm going to go ahead and do, so that's going to give us minus sine of x. We still need to integrate this term, sine squared times cosine. And then now here we can make a u substitution. Namely, u is sine of x. And then our du gives us cosine of x dx. And so our integral becomes minus sine of x on the outside times the integral of u squared du. And then finishing that guy off isn't too difficult. U was sine of x. And so this is how all of these types of integrals are going to go. You're trying to integrate trigonometric functions, and you're given products of trigonometric functions with various powers. You want to look to manipulate those powers in terms of changing some back and forth using your Pythagorean identities, and then looking to make a u substitution. So let's see a couple more. Say we want to integrate sine to the fifth of x times cosine squared of x dx. So what do we want to look for here? We've got just sines and cosines again. So sines and cosines are easy to convert back and forth to each other. They also play nicely with each other in terms of their derivatives. However, one thing we always want to look for is to have like one lone power of one of the trig functions left over. That is for the differential, right? Just like in the last one, we had 3 powers of cosine. So we left 1 there, converted the other 2 into sines. Then when we make our u sub as sine, that last cosine gets substituted out. So our substitution here, if we converted all of our cosines, we've got 2 powers of cosine. If we converted those to sines, well, then I'd have all sines, which doesn't quite help, right? If we make that u sub, the derivative of sine is a cosine. So we would need at least 1 power of cosine. Conversely, if we look at our sines, we have an odd power of sines. So we can pull one of those guys out. Let's write it as sine to the fourth of x cosine squared times sine of x dx. So I'm thinking ahead, and we kind of see this term as sine of x dx. That is the derivative of cosine up to a minus sign. So what we want to do, if I can convert all of the other terms to cosines, will be good. Then I can make a u sub for cosine, and then this will be my differential. So now we have 4 powers of sine. Let's go ahead and convert those to cosine, again, using our Pythagorean identity. So sine to the fourth of x is just sine squared of x squared cosine squared. And now that sine squared, we can convert to 1 minus cosine squared of x. All of that is going to need to be squared. But now we can see we have all cosines, constants sometimes show up, and then that extra power of sine will work in our differential. So a little bit of algebra that we have to work out before we can actually integrate. So square this term out. We're going to have to distribute this other power of cosine. So what do we get? Cosine squared minus 2 cosine to the fourth x plus cosine to the sixth x all times sine of x dx. And now our last step, we have all powers of cosines with one lone sine. So now we can make a nice substitution. U is cosine of x. And then du is going to be minus sine of x. And when we make that substitution, now we got u squared minus 2u to the fourth plus u to the sixth. And then all du, and we need an extra minus sign in there. So I'll go ahead and flip all the signs. Integrate. And then last step, just to back substitute. So our u was cosine of x. Any questions? Sorry, I'm just now seeing some comments in chat. If I ever miss something, did I miss a minus sign somewhere? Integral of cosine? Yeah, I did that wrong. Looks like I missed a minus sign. Just speak up if I miss a minus sign, or if you guys want to talk about it in chat and catch all my little mistakes. Yeah, integral of cosine is positive sign. So all of these signs should have been positive. Always be careful with that, of course. We're doing both integrals and derivatives of sines and cosines. Easy to have some brain farts. Okay. Let's do one more fairly easy one. Those past two were easy. Why were they easy? Well, the powers of sine and cosine were kind of cooked up nicely enough so that it was fairly straightforward. We could convert the necessary number of sines and cosines to one or the other, and we always had that one lone term that we could then take care of in the differential. So let's see. We should have another easy one here of, see, tangents and secants. We'll see a lot of. So we've got the integral of tangent to the sixth and secant to the fourth of x dx. So what do we want to do in this case? We see secants and tangents, and we've got our powers there. So let's write out our notes again, at least for these functions. Our 1 plus tangent squared is secant squared. Or you can write it as tangent squared is secant squared x minus 1. So that's the Pythagorean theorem, or the Pythagorean identity, that relates these two functions. And then we also know that the derivative of tangent is secant squared, and the derivative of secant is secant x tangent x. So these two functions related both in their Pythagorean identity and in their derivatives. We just need to play around with those to try to see if we can get a nice U sub. So these ones are a little bit different, right? With sines and cosines, we need to convert everything to one function except one power. As in the examples we saw, we want to leave one power of cosine or one power of sine, convert all the other powers to something else, to the other version. Secants and tangents are a little bit different, because if I want my u to be tangents, if we want to substitute out our tangents with our u sub, I need to have two powers of secant remain for the differential. With secant, if we want to make our u sub as secants, well, we actually need to leave one power of secant and one power of tangent to substitute out in the differential. So sometimes one works, sometimes the other doesn't. And so you just got to get used to practicing some of these. So you want to look at your powers and try to find a way to break it down, and almost work backwards is kind of how my brain works when I look at these. I like to start with tangent. Anytime I see tangents and secants, I always kind of look ahead thinking that I want to substitute out tangent as my u, and then try to see if we can make that work. So let's think ahead a little bit. If I want to make a substitution for tangent, we need to leave two powers of secant. So if I leave off two powers of secant, how many powers of secant do we have left? So we can write it out. So these are going to be the terms that we leave off for our differential if we make tangent our substitution. But I have how many powers of secant left? 2. Does that work? Does that help us? Well, that's when we go up to our Pythagorean identity. 2 powers of a trig function is always nice. All of these Pythagorean identities always involve converting a square of a trig function into another trig function. So namely, I can convert these 2 powers of secant into 1 plus tangent x. And in that case, everything that remains will be tangents, powers of tangent. So let's go ahead and do that. I convert those 2 powers. I leave the 2 powers of secant there with the differential. We can go ahead and distribute. Mind your parentheses, right? That secant of x is being multiplied by both terms, which of course we need in order to make a correct substitution. And so now we see we have only powers of tangent and the derivative of tangent sitting in the differential. So that gives us a nice u substitution with tangent of x. So we'll have u to the 6 plus u to the 8 times du. And now we have an easy enough integral. So we integrate and then back substitute. So as a check with all of these, you can take a derivative, right? Anytime you're doing an integral, especially if you've got time on tests and quizzes, highly recommend you guys take the derivative of your answer. So practice going back through that, taking the derivative of your answer. It'll help you review the chain rule a little bit, and you should be able to manipulate it back into the form that the integrand originally appeared. Again, if we take a derivative as is, we'll have some chain rules involved, and it might look something more like this, and you might have to then go back through and reverse engineer the substitutions we made in terms of the Pythagorean identities to get it to look as the original integral. But that's all good practice. I would say good habits to get into, easy ways to check if your homework's right, and especially on tests and quizzes, since you only get one shot at those, always make sure you're checking your work when you got the time for it. Any questions on this? Okay. Excuse me. So let's take a look at some slightly more difficult ones. And these are the ones that have weird and wonky powers where we can't divide up the powers of the trig functions nicely enough to give us this nice differential term to make our substitution work. So that is kind of the crux of all of these. Let me see. Easy one, basic one to start with is something like sine squared. But then you can do something like sine to the fourth or cosine to the fourth. All sorts of examples. Let's do sine squared. So what's problematic about this? Again, when we have sines and cosines, it's really nice when we have an odd power of one of them. Whenever we have an odd power of sines or cosines, we can always leave that one off and convert the even number or the even power of sines and cosines into the other one. So here we converted an even number of cosines into even number of sines. And then in the next one, we have an odd number of sines. We leave one off and we convert the remaining even number of sines into cosines. And now notice in this one that the cosine squared actually didn't matter much. The powers on the cosine. If this were cosine cubed or if this were even or odd, it actually doesn't matter as long as at least one of them is odd when we have sines and cosines. Because then that one odd that we can use, we can leave off the one, and then we have an even number that I can convert into the other trig function. And so problems arise really only when we are given an even number of sines and cosines being multiplied. So what do we have to do in these cases? In these cases, we have to do some fancy tricks. There's two ways to approach integrating sine squared. We can either do integration by parts, or we can use a half angle formula. So off the top of your heads, who remembers the half angle formula? Basically what I thought.
Is it 1 minus cosine of 2 theta over 2?
Yeah.
Half angle, yeah.
Yeah. So one person knows it. Couple people know it in chat, looks like. Yeah. So you can use the half angle formula, which works reasonably nice. And it's pretty quick. The other thing you can do is do integration by parts. So since we've done integration by parts, let's go ahead and use that technique. And then maybe we'll use the half angle formula or double angle formula. And I'll mention how to do it and leave that to you guys if you want to use that on your own. Again, using integration by parts, it's going to be a little tricky because we got to use combination of things. So our integration by parts, sine squared is sine times sine. And we know how to both integrate and differentiate sine. So if we make one of the powers of sine our u, and one of the powers of sine dv, we can use that pretty easily in the formula for integration by parts. So again, be careful with your minus signs on all these. We are both integrating and deriving sines and cosines. And so what do we have? Our integral of sine squared is going to be sine x cosine x minus the integral of cosine squared x with a minus.
Shouldn't we have a du at the end of the, yeah. Sorry, dx.
Yeah. Okay, well now we're in another situation. How do we integrate cosine squared?
It's the same half angle formula, just with a plus instead of a minus.
Use the half angle formula. Yes. So if you know the half angle formula, you're going to use it right at the beginning. No reason
you
to
just
do.
use the boomerang trick that we used the other day, because you're just going to get negative sign again, and then you can just take out the negative and then use the boomerang trick.
Boomerang trick. Yeah. So the boomerang trick is going to work. What's going to be bad if we try integration by parts again here with cosine? What's going to be bad with that? Anyone know?
Wouldn't this be -2 cosine x sine x, which would just not help us at all?
-2 cosine x
If
sine.
you would have to set u equal to cosine squared x, which when you try to do like u times v minus the integral of v du, it just won't help us, right?
Yeah, so everyone's saying some good things. If we
Could be
try
wrong.
to make u equal to, we would almost have to try a different u in dv. So I mentioned yesterday, whenever you have these cyclic functions, you kind of have to make them the same substitutions. Otherwise, you can end up going backwards. So if we tried this again with kind of the similar substitutions as u as cosine and dv is also cosine, then when we completed the integration by parts formula, it would end up taking us backwards. We would actually ultimately get something that would cancel this out, and we would get integral of sine squared x equals the integral of sine squared x, which doesn't help us at all, right? So you would have to play around and try different integration by parts, either making u equal to cosine squared of x, and then when I would integrate dx, well, now I'm introducing polynomials to the fray, and we would get an x. So let's write some of this out, since all good ideas. And since I do want to illustrate the process of things that can go wrong when trying to guess integrals. So let's keep a star here to try to keep our notes organized. And let's just write down our things we want to try. If we have our u as cosine x, our dv as cosine x dx, our du is minus sine x dx, and v is sine of x. And so if we plug that in the formula, what do we get? We still have this minus sine x cosine x plus a sine x cosine x. That's our uv. And then a minus the integral of v du, which is just sine squared x. And then with that minus gives us a plus. And so you can kind of see those two terms are going to cancel, and we will have sine squared x equals sine squared x. So no help. Well, if that didn't help, someone else mentioned, well, if we try to do u as our entire cosine squared x, we can at least take a derivative of that. But what happens with our du, or excuse me, what happens with our v? So our du is going to be 2 cosine x sine x, which will be negative. But then our dv is just dx, and then our v ends up being x. And so now we're going to get something like the integral of v du, which is now 2x cosine x sine x. And is this an easy integral to do? No, right? Now we have not only trig, but we also have polynomials in there. So that would require, again, another integration by parts, and then you might end up going in circles and going around backwards again. So again, no help. So whenever you're in a situation like this, if you try an integration by parts, like especially in this situation where we end up just going backwards, we get back the thing we started with, look for a substitution. So what we actually want to do at this location, so at our star, is I have a cosine squared x, and if again we're trying to couple integration by parts, not helpful. We want to look for a trick in some way, a substitution of some sorts, and we can actually convert our cosines back to sines, and that's what we're going to end up doing. So we can write the integral of sine squared is sine x cosine x.
I think you're off the Zoom view.
Thank you. So integral of sine squared x is minus sine x cosine x plus our cosine squared x. So that term I'm just going to write as 1 minus sine squared x. And how did that help us? Well, now we can do the boomerang trick. So integral of 1, I'm just going to give us x minus the integral of sine squared x dx. And so I can add this entire integral over to the other side to get 2 sine squared of x equals this guy. So ultimately we will get the integral of sine squared x dx is equal to minus sine x cosine x plus x all over 2. And we should say plus a constant. So this is how we deal with even powers. The other way, as mentioned, was the half and double angle formulas. So some people sound like they know those, or you can look them up. On homeworks, of course, that's going to be great. It's easy to look up a formula. However, you may not remember it on a test. So some helpful tips if you do want to do that way. Since we are reviewing a little bit of trig formulas here, these Pythagorean identities, you guys are Calc 2 students too. So you guys are a bit more advanced. And so hopefully these won't be too problematic for you. I know pre-calc students get a little bogged down with formulas and can't memorize it all. I tell students that there's only 2 formulas you need to remember for trig. You need to remember the Pythagorean theorem, cosine squared x plus sine squared x equals 1. I think that one almost everyone always knows. And then the other one that's easy to remember that can help in these situations is cosine squared x minus sine squared x is the double angle formula. So from these 2, you pretty much can then derive any useful identities, right? Like we had 1 plus tangent squared of x equals secant squared. You can always take this equation, divide everything by cosine squared, you'll get a new trig identity. You can divide everything by sine squared to get a new Pythagorean identity. Likewise, you can use the Pythagorean identity coupled with this guy to solve pretty easily for half and double angle formulas. So for example, when we want to do the integral of sine squared x, if all you remember are those 2 and your algebra skills are good, which they should be for Calc 2 students, if I want sine squareds, let's just make everything in this equation, or at least on the left-hand side, sine squared. Here, let's label these. Let's label them 1 and 2. So let's take equation 2, and actually here, we'll put 1 into 2. Let's convert our cosines into sines. So we will have 1 minus sine squared minus sine squared is cosine of 2x. And so 1 minus 2 sine squared x is cosine of 2x. And now all we got to do, what do we want to substitute out? Our sine squared. So let's solve for that. So that's our sine squared. And now it's an easy enough substitution. And then we can do the integrals. I like to keep the powers of 1/2 out front. It's much easier for me to organize the work. So I'm just going to pull that out of the integral. So our integral of sine squared is just 1 minus cosine of 2x with that power of 1/2 pulled out front. And now we can integrate. You can use a u sub for that inside term if you want. Or you can just, doesn't leave space there, but we need to divide by that power. Since it is a constant, it's easy enough to just integrate from there. And then, so what is our answer we got here? So 1/2 x minus 1/4 sine of 2x plus c. And as astute Calc 2 students, what do you notice between these two techniques? So we tried it one way, integration by parts. We tried it another way by the half angle formula. Are those two answers the same?
Yeah, because sine 2x is 2 sine x cosine x.
Yeah, there you go. So good check. If you get different answers with different techniques, try to substitute one. We can substitute the sine 2x back into sines and cosines. And then sometimes there's just a difference in terms of the constant that can arise. So good check. All right, so any questions on this? So that's it for these trig integrals. Those are all the basic techniques. Again, I think the crux of it is looking for that differential, thinking ahead, being able to use, let's go back to the tangent one and take a look. Right, whatever your integral is, whichever trig functions arise, maybe it's helpful to write down your relevant formulas, both in terms of the derivatives and the Pythagorean identities that relate those. And then you always want to think the derivatives are important because those give you your differentials. All right, so always kind of think ahead. If I want to make a tangent substitution, I need to have 2 powers of secant. So you kind of want to look, can I factor out and keep 2 powers of secant and then convert the rest to tangents? And vice versa. If we wanted to do one with secant, I need 1 power of secant, 1 power of tangent. That's what you're going to want to peel off and factor out and keep with the differential. And then try to see if you can convert then everything else into secants. And it works that way with all the trig functions. Okay, so let's take a quick break for 5-10 minutes. And then when we get back, we're going to get into trig integrals. We're actually going to be using these Pythagorean identities a little bit more and seeing how we can integrate more complicated expressions. These often involve expressions of having sums and squares, squared terms, quadratic terms underneath a square root. And so a priori, when we're doing u subs, they look like a mess. They don't seem very natural in terms of how we can be able to substitute that out. And so we'll see how we can use these trig identities to make those simpler on ourselves. All right, so let's go ahead and pause the video and take 5. All right, so let's get back into it. We only got 10 minutes or so here. We were just talking about some of the homework stuff. Let's take a look at how else trig identities are going to be useful for some of these problems. And let me go ahead and pull up my examples here. Let's see. All right, so let me switch my video. So a lot of these, we want to lead by example. Let me refocus that here. There it goes. So suppose we want to integrate, and let's do something easy. Let's do a definite integral. So when I say easy, I really just mean easy if you know the tricks. So let's say I have a function, something like the integral of 9 minus x squared underneath a square root. So how do we do something like this? Our u subs aren't going to work because if we substitute out something on the order of x squared, then the differential will have an x in it, right? It'll have x dx up to a constant, and we don't have another power of x. So u sub isn't going to work. The next thing we think of is integration by parts. Okay, well, integration by parts, this is where it gets a little hairy because, well, I can't integrate that square root, so we would have to derive it. And I mentioned a little bit before, what happens when we take derivatives of square roots? We get more square roots, right? They never go away. We can keep deriving and deriving, and we'll get different fractional roots. And not only that, we will have a chain rule, so we'll have extra powers of x coming out from that. So sometimes those work. That might end up working with a u sub after that. But this gets in a little bit in terms of, well, what are trig based off of? Where do they come from? They come from the unit circle. So what is this function? If we were trying to graph this, the function square root of 9 minus x squared, what is that? Anyone know?
Circle with radius 3.
Circle with radius 3. Good. So this integral we have a geometric intuition for. Namely, I want to find the area underneath the circle of radius 3. And in particular, since we have a positive square root, we're taking the positive half of the circle, the top half. And then if I'm integrating my x's from 0 to 3, we are looking for that area. So what is that area? Area of a full circle, of course, pi r squared. So let's call this, let's give it a different letter. Let's call it B as our total area. So our B is going to be a quarter of a circle, so 9/4 pi. Great. We can use some geometric knowledge to figure out the integral just based on the area of nice shapes. But it's not always that case, right? We often see integrals just like this. This could have been in the denominator. We could have tried to integrate 1 divided by this, and we would run into the same problems. And now if we're trying to integrate 1 divided by this square root, we don't have as nice of a geometric intuition. So how do we do this, and how do we go about doing it? So that's our question. So how to integrate? We'll use our geometry as a check, we should get this as the answer. And our idea is to use trig identities to convert the sum. Here, we don't really want to convert. Let's say to get rid of the sum. Underneath the square root. That's our biggest problem, right? We can integrate square root. If it was square root of x cubed, we can integrate that easily, right? We can just convert everything to powers of x and use the basic power rule in terms of integration. It's really that sum that is screwing things up. And not only that, that sum with a higher power of x, namely the x squared. If it were just square root of 9 minus x, then a basic linear substitution, a u sub, will work in that case. But as we mentioned, as soon as we have an x squared, we try to make a u sub, and, well, I don't have the correct differential outside of that square root to work with. So we mentioned our Pythagorean identities. Let's write them in slightly different forms. 1 minus sine squared x is cosine x squared x. 1 plus tangent squared x is secant squared x. Those are the main ones. I'll leave it to you guys to write out the other ones if you want, in terms of cosecants and cotangents. Of course, and then we can always just switch these guys around. 1 minus cosine squared gives us sine squared. Secant squared minus 1 gives us tangent squared. But the nice thing about these identities we see is that it is a sum or a difference of two terms. It's a sum and difference of a constant and a square of a function. And then the other side of the equation is just one function. And even nicer enough, it is a square of a function. So squares of functions are going to play really nicely with these square roots. So if we wanted to get rid of a difference of two terms, maybe we can take advantage of the fact that these trig identities convert a difference of terms into just a single term. And then that single term is going to play much more nicely with a square root. So we got to do a little bit of algebraic manipulation here because we have a constant here. Well, that 9, right? It's not a 1, but constants aren't too terrible in terms of dealing with them. So we've got our integral from 0 to 3, square root of 9 minus x squared dx. And so what do we want? We want the inside to be something like 9 minus 9 sine squared x. Why do we want that? Well, we like 1 minus sine squared x. What happens if I multiply this entire equation by 9? We get 9 minus 9 squared x, or excuse me, 9 minus 9 sine squared x. And we can convert that to 9 cosine squared of x. So that's all we need to do to deal with that constant, is really multiply our trig equations by that very constant and see what would be nice for us to have in order to use that identity. And so if this is what we want, and actually, sorry, let's change the variable here. Since x was our given variable, let's make this a theta for our angle. So if this is what we want, how do we get that? Well, I have an x squared. I need that x squared to be 9 sine squared of theta. So this is how I walk through these substitutions. For me, it's easier to kind of think in reverse of what do we want? What would make it this usable in terms of a trig identity. And then just write out the equations you need to get there. I need this x squared term to be 9 sine squared of x. So what does that tell us our substitution needs to be? That's saying that we want to make x 3 sine of theta. And of course, you get that just by taking a square root of both sides. And so this is going to be our substitution, just like we would do in a u sub. Sometimes we write it as u is equal to, whatever functions of x we want. I don't know if your instructor showed it to you when you guys were learning it, but you can also kind of solve the other way around. And sometimes it's necessary to do so, to solve for your x in terms of what do you want to make x into in order to make your substitution work. So that'll make our substitution work. The other piece we need is our differential. So our dx is going to be 3 cosine theta d theta. And so now let's go ahead and make that substitution. Our integral is going to become the square root of, well, we already cooked this up nicely. What is x squared? 9 sine squared theta. So we'll have 9 minus 9 sine squared theta. And then our dx is going to be 3 cosine theta d theta. And just like when we do u subs, you got to make sure you're changing the bounds. And again, 2 ways to do it. You could do the entire problem, then back substitute once you finish the integral, back substitute for all your x's and plug in your x bounds. Or the way I like to do it is to just find the bounds in terms of theta. So got to remember all your trig. This is why we have those first couple of problems on the homework set. Just remember how to evaluate trig functions. When x is 0, I will have 3 sine theta equals 0. Sine theta equaling 0 means theta is going to give us 0. Our other one we can check. So when x is 3, if we wanted to write it out, we will have 3 is equal to 3 sine theta. Sine theta equals 1. And so our theta is pi over 2. So that's our upper bound here. So that's a little interesting too. Look at kind of what we did. I'll give you a little hint of what's going to be coming here, I think later in the semester when we get to polar coordinates. What's our angle here on the x-axis? If this were a unit circle, the angle on the x-axis is 0. And then if we were to kind of think of this as, radially sweeping counterclockwise like we do on the unit circle, we want to go here, and then we want this whole area up to this part, right? You want to stop here. What angle is that? Pi over 2. So our bounds make sense in terms of our substitution and in terms of the angular degrees, or I should say the angular radians of the circle that we're trying to compute the area of. And now we just have to finish the integral. So let's take a look at what we've got. We still need to use our trig. So we're about out of time. Let's go through this a little quickly, and we can start here and review it tomorrow where we start. The 9, what we want to do is factor that out. So we can write it as the square root of 9 times 1 minus sine squared theta times cosine of theta, 0 to pi over 2. The square root of 9 is going to give us another power of 3. So we'll have 3 times 3 as our constants. 1 minus sine squared is cosine squared. Square root of cosine squared is 1 power of cosine times our extra power of cosine. And now we see our integral of 9 times the integral 0 to pi over 2 of cosine squared. And so now we're back at our previous techniques. We see why these trig integrals end up being important. So integral of cosine squared, let's go through real quick. Again, write out those formulas, manipulate them if you need to learn the half and double angle formulas. Or again, you can use integration by parts here if you'd like. Cosine squared is 1 plus cosine 2 theta times a half, all of that times a half. And so our integral 9 halves. We have the integral of 1 plus cosine of 2 theta. So we will have theta plus 1/2 sine of 2 theta as the integral. And we got to evaluate that between 0 and pi over 2. When we plug in our pi over 2, we get pi over 2. What's sine of pi? Just 0.
0.
Yep. And then 0, when I plug in, we'll give a 0. And what is sine of 0? Sorry, that should be a minus. When we evaluate at 0, we just get zeros. And so our net result, 9 pi over 4. And that is exactly what we wanted from our geometric reasoning. Any questions?
Yeah, I have a quick question. So, could we do this even if this wasn't a definite integral?
Yeah, exactly. So even if it wasn't a definite integral, you could go through these techniques, and then what we would have essentially after we did the integral would be terms of theta, and then you just back substitute. We'll work on those tomorrow. I wanted to give a definite integral to start off with, just so we could geometrically find that answer and check ourselves, so that we kind of see what we're doing. But we'll see a lot of examples like this tomorrow.
All right, thank you.
This might be a really simple question thing that I'm missing here, but how did you turn the cosine? Oh, is that just a trig identity with the cosine of 2 theta that turned in? Oh no, so the cosine of 2 theta turned into 1/2 sine of 2 theta, and I'm just confused why.
It's the integral of that.
Oh, I was taking the derivative accidentally. Okay, yeah.
Other questions?
What time are your office hours today?
Office hours 3 to 5 today.
Cool, thank you.
All right, I'll see you guys tomorrow, or in office hours if you want to stop by.